Okay, now again, just quickly reviewing what we did last time. If I've got a rubber band and I stretch it out a little bit, creates a tension in the rubber band. Okay, and that tension, of course, tends to pull the rubber band back toward itself, but it tends to pull my fingers back toward each other. And the further I stretch it, the more tension there is. Now you can think of this rubber band as being two strands, doesn't matter how far apart they are, and even if you kind of twist them and melt them together or something, you get the same force as you would if they're separate. The key idea is that if I have these together, I've essentially got a rubber band of the same material that's got twice the cross-sectional area. If I take the cross-section here, I have the cross-sectional area of this part plus the cross-sectional area of this part. And if I add another rubber band, I've got 4 times the cross-sectional area of any one of the strands. So if I sort of combine this without twisting it too much, because that affects the cross-sectional area, but now I have 4 times the tension for any given change in length. So when you get the idea that the tension response is proportional to the cross-sectional area. So if I have a thicker rubber band of the same material, I can calculate what the tension force would be if I know the cross-sectional area here and the cross-sectional area here and the force exerted by this rubber band at the same length, assuming the 2 rubber bands have the same basic length, which they do. Okay. So if they have the same cross-sectional area and the same tension, but let's now say that one of the rubber bands is longer than the other, or let's say maybe we do this. Okay, here we got the 2 individual rubber bands. They both have their tension response, but we chain them together to make a rubber band with the same cross-sectional area, but twice the length. Now a little less than twice the length because of the knot we have there, but yeah, just assume it's got twice the length. Okay, to get the same tension, each rubber band has to have the tension that one rubber band did before. Okay, there's no significant weight. We can regard at least the weight of the rubber bands as negligible compared to the tension. Okay, so that both of them have to stretch out to give me whatever tension I have here, as far as one of them would have to stretch out. Meaning that if I exert the same force to pull them apart, I have to stretch them out twice as far, stretch this system out twice as far as I would this system to experience the same force. Okay, so if you got rubber bands, the same material, same cross-sectional area, to get the same tension, the longer rubber band will stretch more than the shorter rubber band. And the stretch will actually be proportional to its length. Now that's a big deal, and we want to understand that. Okay? So, if you have the same length and the same tension, then a rubber band with greater cross-sectional area is going to stretch less. Okay? Because same length of rubber band, same tension, the same force is going to stretch it out less. That's all there is to it. That should be pretty clear. So it requires more stretch. Another way of saying it is that the rubber band with greater cross-sectional area will require more tension to stretch by the same amount. Play around with rubber bands. Convince yourself of these proportionalities. Okay, so stretch depends on the tension, cross-sectional area, and length. In symbols, let L be the length, and let L be, yeah, okay. Not being very specific here. I might want to let L yeah, it'd be consistent if I did this. I'm going to say let L naught be the maximum unstretched length. Okay, and I say maximum unstretched length if I'm thinking about rubber bands. You know, you might regard the length here as being less than the length if the thing is all pulled together, but with no tension on it. So, you know, the length here is a little greater than the length here if you consider length as the distance between the two ends. So that's why I say maximum unstretched length, but we could just say unstretched length if we want. Okay, so let L naught be the unstretched length and delta L the amount of stretch. Then if T is the tension and ACS is the cross-sectional area, then the delta L is going to be greater for greater tension. It's going to be greater if your L naught is greater, your maximum stretch length. It's going to be shorter for greater cross-sectional area. So we have the proportionality that maybe delta L is proportional to the tension and to the L naught, the maximum unstretched length, and inversely proportional to the cross-sectional area. That is, you keep for the same length and cross-sectional area, if you double the tension, you're going to get twice the change in length. If you fix the amount of tension in the cross-sectional area, then you're going to get a greater delta L for greater initial length. And if you have the same tension and the same initial length of two rubber bands, one with a greater cross-sectional area, say double the cross-sectional area, then the one with double the cross-sectional area is going to have half the delta L. Okay? So, easy enough to see the proportionality between, for a given length and cross-sectional area, directly proportional to T, is not as obvious, okay? In other words, as we said, if you got twice the initial length, you're going to get twice the change in length. If you got twice the cross-sectional area, you should get half the change in length. That's just common sense, almost. You got to verify it experimentally. You can't just think that your common sense really is all that sensible. But that's easy to verify experimentally. So is the other thing. If you have a direct proportionality to the tension, so the doubling the tension does give you double the delta L, then you have what's called a linear restoring force, which of course is what gives rise to simple harmonic motion and so forth. Rubber band is not a real good example of that. Okay? If you have a direct proportionality to T, then your graph of tension versus length should be a straight line. Okay, that would be a direct proportionality. You don't have that for a rubber band. For a rubber band, I've exaggerated the curvature, but it does go pretty much along curve like this. First start stretching it, takes, it's a little tougher to stretch, but then it gets kind of easy to stretch, but then you get out to the nearer the breaking point and it gets harder to stretch again. It's not ideal, and nothing really is, but many materials like a high quality steel spring or high quality steel or a lot of other materials are very close to ideal, and anything is close to ideal as long as you don't stretch it too much. If you have the rubber band and only consider lengths between this length and this length, it's pretty much a straight line. Okay, well, in any case, for an ideal material, and I wrote delta L is proportional to L, but delta L should be proportional to the tension, all other things being the same. Okay. Ideally, then, your delta L should be some constant times the product T times L over cross-sectional area. So that delta L over L naught is this, just doing a little arithmetic. Your tension then would be 1 over K times your cross-sectional area times your delta L over L naught. And these are just algebraic rearrangements. You end up then with tension over cross-sectional area equals 1 over K, where K is this number, times delta L over L naught. And what's delta L over L naught? You can estimate delta L over L naught. Here's length, here's a rubber band. Okay, it's got a length. Okay, now I'm going to pull it further apart. Okay, well, it looks like I pulled it about 25 or 30% further apart. Delta L is then 25 or 30% of the original length. So delta L over L would be, say, 0.25. If I exert the same tension on a rubber band that's got more length but the same cross-sectional area and same material, okay, I still would expect a 25% change. Okay, so this delta L over L is actually something that we call strain. Okay, it's how much the thing is strained. Okay, the tension over cross-sectional area, well, we can think of that as tension per square millimeter. Okay, newtons per square millimeter, newtons per square meter, newtons per unit of area, force per unit of area. Okay, cross-sectional area, and that's this quantity, tension over cross-sectional area, and then we call that stress. This K I had here, it's reciprocal then, according to this, is equal to stress over strain. And this is what we call Young's modulus. Now the terminology your book uses, or the symbolism your book uses, is E for Young's modulus. Now, there are only so many letters, and E is awfully easy to confuse with energy, and energy is kind of involved in this thing as you stretch something apart, especially if you're going to get simple harmonic motion. So I'm not sure E is the best letter to use. I don't think I would have chosen it, but I'm not going to question the authors of your text who know way more than I do and are probably much more consistent with standard usage. So ignore me and we'll go with them, but be cautious that we understand that this is not energy. This is called Young's modulus, and it's stress divided by strain, where stress is the Greek lowercase sigma and strain is the Greek lowercase epsilon. That's the notation you're going to see. And that's coming up in this week's assignments. So tension per unit area is your stress. It's tension per unit area. Strain is stretch per unit of length, amount of stretch per unit of length. The units of your stress are units of, well, tension over cross-sectional area. I said it before, force per unit area. So it's units of force over area. Force over area units are pressure. And I demonstrated this last time. If I squeeze this thing using the incredible strength between my fingers, I'm exerting a pressure on it. And that should shorten the length of this column of chalk. Okay, you don't want to do too much or the chalk explodes, so I'll be careful not to do that. But we have a pressure that causes a negative change in length. If I pull this way, well, that doesn't seem like a pressure, but it still has units of pressure of, again, tension per unit of area. Okay? I hope I wasn't saying per unit of length. It's, you know, force per unit of area, compressing, force per unit of area, stretching. Force per unit of area is pressure. Okay? Even if you're stretching, it's got units of pressure. If you're compressing, it seems like pressure. Okay, well, stretch per unit of length is unitless because it's a change in length, which should be in units of length, divided by length, which is in units of length. And there it is. Okay, so I'm going to talk a little bit more about that. Wes, I know you're probably getting near the end of your hour, so I'm not trying to run you off. Stick around as long as you can, but when you disappear, we'll miss you, but we'll have it on video for you.
Appreciate it.